Hello everybody. In this video, we're going to look at understanding a geometric distribution. So a geometric distribution is when we look at the number of times it takes for something to happen for the first time. And for it to be modeled geometrically, then it needs to obey two conditions. The first condition is that the trials must be independent. And the second condition is that there must be a constant probability of success for the different trials. So if we look at an example here, a third dice is thrown and the number of throws it takes to throw a 4 is recorded. So if you were to get a 4 on the first time you threw a dice, well, that would be a probability of 1/6. But let's say you didn't get a 4 on the first throw. Let's say you got it on the second throw. Well, that must mean that you had to have failed your first attempt, and then you would have got a 4 on your second time. So that would be 5/6 multiplied by 1/6. So we can write this down using the distribution that x is modeled geometrically with a probability of passing at 1/6. And whenever we write a model like this, we need to define the random variable. So we'll say, let x be the random variable, the number of throws until a 4 is recorded. So the probability of getting a 4 on the first time is when x equals 1. And this will just be 1/6. The probability of getting a 4 on the second time would mean 1 failure on our first attempt and then a pass. And getting a 4 on our third attempt, well, we would have had to fail on our first, fail on our second, and then pass on our third. So this will be 5/6 multiplied by 5/6 multiplied by 1/6, or 5/6 squared multiplied by 1/6. So we can generalize this as the probability of x being any observed value will equal the probability of success, in this case 1/6, multiplied by the probability of failing to the power of the total number of trials minus 1. So if we look at question A, the probability of x being the observed value 5, well, this will be 4 failures, so 5/6 to the power of 4, and 1 pass. And this gives us 0.0804. For B, the probability of our observed value being equal to 8, well, we must have had 7 fails, so 5/6 to the power of 7 multiplied by the 1 pass. And this gives us 0.0465. And then for C, the probability of getting a 4 after the 6th attempt means we must have had 6 fails. So the probability of x being greater than 6, well, if we've had 6 fails, this will be 5/6 to the power of 6, which gives us 0.3349. And then for part D, getting a 4 after 10 or more attempts, well, we could get it on the 10th attempt, which means we would have had 9 fails. So this will be the same as the probability of x being greater than or equal to 10 will be 9 fails, so 5/6 to the power of 9, which is 0.1938. Okay? And in example 2, we're going to look at the cumulative geometric distribution. Okay, so now we're going to look at the cumulative probability of a geometric distribution. So if we're looking at the probability of our random variable x being less than or equal to any observed value, so this will be the probability of our observed value equaling 1, so it happens on the first occasion, plus the probability of it happening on the second occasion, or it could happen on the third occasion, and we will keep adding these up until we get to our observed value. So we'll add one more, the probability of our observed value equaling 4, and this would carry on. So the probability of our random variable equaling any observed value would be this probability, which is P so it happens on the first time with no fails, or it happens on the second time, and if it happens on the second time, we would have had one pass and one fail. If it happens on the third time, we would have had one pass and two preceding fails. On the third time, one pass and three fails. And again, this would carry on. But can you see that now we have a geometric series where the common ratio is going to be 1 minus p. And the first term, this p here, would be the a term in this formula. So a will equal p. The common ratio will be 1 minus p. The n term would be our x, of the observed number of outcomes. And the sum of the series would be the cumulative probability. I should have written this here as well. Okay. So now all we need to do is substitute these values into this formula. And we should be familiar with this formula from year 2 A-level maths. So the probability of our random variable being less than or equal to any observed value will be a, which is p, multiplied by 1 minus r, so 1 minus p, to the power of x, all over 1 minus r, which is 1 minus p. And now we can tidy this up by expanding out these brackets. And when we do this, we get the negative 1, which will cancel with this positive 1. And the negative p will become positive p. So we get p lots of 1 minus p to the x all over p. And then this p will cancel with this 1. So we're left with the probability of our random variable being less than or equal to any observed value is 1 minus p to the x. Okay? And in our next example, we're going to use this formula to calculate cumulative probabilities. So in example 2, we've been told that the random variable y is distributed geometrically with a probability of passing 0.4. And we've been asked to find the probability of passing on or before our 7th attempt. So we can use this formula where our observed value will be equal to 7. So we'll have a probability of y being less than or equal to 7 will be equal to 1 minus p. So 1 minus 0.4 raised to the power of x, which is, in this case, y and 7. So then this would become 1 minus 0.6 to the 7, and this is 0.972. For question B, the probability of our observed value being less than 10. Well, if it's less than 10, it cannot be 10, but it can be 9 and 8 and 7 and so on. So this will be the same as the probability of y being less than or equal to 9. So this will be 1 minus the probability of failing, 1 minus p, 0.6 to the power of 9. And this gives us 0.9899. And for C, so in question C, we're looking at passing after our 3rd attempt, but up to and including our 8th attempt. So the best way to understand this is to write a list of these different attempts. So what we're looking at is including the 8, but not including the 3. So all of these. And this will be the probability of y, our observed value, being less than or equal to 8 minus all of these. So probability of y being less than or equal to 3. We can work out being less than or equal to 8 as 1 minus 0.6 to the 8. We'll put this in brackets, minus the probability of y being less than or equal to 3. So 1 minus 0.6 to the 3. And when we work this out on our calculators, we get 0.199. And for question D, again, I'm going to write the list from the 1st to the 12th or more outcomes. So we're told the greatest number of times it can happen is 12. So we'll start at 12. And it can happen on the 5th attempt. So we'll include the 5. So this will be the probability of y being less than or equal to 12 minus the probability of y being less than or equal to 4, which is all of these. And we can work this out as 1 minus 0.6 to the 12 minus 1 minus 0.6 to the 4. And on our calculators, we can do this and we get 0.1274. Okay? So we're going to try one more question which places this in a real life context. So here we've got a typical exam question. In example 3, we're told that Marie is playing a board game with a fair 4-sided dice, and she must roll a 3 to start. So it's because she must roll a 3 to start, but first occasion she gets a 3, she starts. This is what makes it a geometric distribution. So because it's a geometric distribution, we can say x is distributed geometrically with a probability of passing 1/4, because it's a fair 4-sided dice. And now we need to define this random variable. So we'll say, let x be a random variable, the number of rolls needed to land on a 3. So for part A, given that each roll is independent, which is one of our conditions for geometric distribution, find the probability that she starts on the 4th go. So we want the probability that our observed value is equal to 4. Well, this means we would have had 3 fails and 1 pass. So 3/4, which is our fail, cubed, multiplied by 1 pass. So 3 fails and 1 pass. And this gives us 0.1055. Okay, so just over a 10% chance of her starting on the 4th go. And for part 2, that she takes no more than 6 attempts to start. So now we're looking at the probability of x being less than or equal to 6. So now we're going to use this cumulative probability here, where we have 1 minus the probability of failing, which is 3/4, raised to the power of 6. And this gives us 0.822. And finally, for part B, state one assumption you have made in your model. Well, we've been told it's independent, so the only assumption could be that the probabilities remain constant. Okay, so thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below. Thanks again, and take care.